Okay, so now that you have your definitions based on how structure can affect acidity, let's take a look at this compound. And I've used the line angle drawings for most everything, but I've drawn specifically the carbon here just because it's connected to that hydrogen. So we want to go with increasing acidity. So we want the least acidic to the most acidic. And what we find is this. If we look at the hydroxyl, we know this is a polar bond. So this is going to have a little bit of acidity because it's a slightly positive charge. We also have resonance if you draw out the resonance form. So you'll find that it has resonance stabilization for the conjugate base. Here, we see that we have basically the carboxylic acid group of acetic acid. So this is definitely acidic. It's again the polar bond, but we also have resonance much greater than here because I also have two oxygens, so it's a more electronegative group. So if I just compare between B and A, B is going to be more acidic than A. So now let's take a look at the CH3. Okay, and let me just go ahead and draw this out more explicitly for you. So what is the C referring to? So the C, we're actually referring to the hydrogen. Okay, so let's compare C to either A or B. And we know that C is going to be less, less acidic. And then we have D, which basically is much closer to electronegative atoms here, like this oxygen. It's not right next to it. It's a carbon and oxygen away, but we do have some effects there. So D would be more acidic than C, which is simply on a CH3 group. The other thing is, bear in mind, when we look at this carbon, this is an sp2 carbon, and this is an sp3 carbon. And because of that, this bond here, that's a sigma S, the sp2 is shorter than the sigma S to sp3. That has an impact on the acidity as well. So what we find then is that B is much more acidic than A, which is much more acidic than D. We still have some resonance here, which is more acidic than C. And so that's how we would use our knowledge of our structures in order to help us to determine which is the most acidic hydrogen. So let's go on to our next topic, which is going to be the definitions for Lewis acids and Lewis bases. We use purple here. So a Lewis acid is one that accepts a pair of electrons to form a bond. So this is different than the previous definitions where we're talking about increasing H plus or donating H plus in an acid base. We are now focusing on the electron movement. So an acid accepts a pair of electrons and the base donates a pair of electrons to form a bond. Usually they're in the form of a lone pair, but sometimes they're in the form of a pi bond. So let's take a look at an example. So here, an example would be this. We're going to identify the Lewis acids and Lewis bases. And the way we do this is you're going to compare your reactants to your products. So if we look at the CH2, it's right here. But now, instead of having a double bond, I have a single bond. So what happened to the pi bond? So this must have donated a pair of electrons. okay, in the form of a pi bond. So who accepted it? Well, the boron accepted it. That's why I have a negative formal charge. So this donates a pair of electrons. This is my Lewis base. If my boron trifluoride accepted those electrons to form this bond right here, then this is my Lewis acid. Now let's look at one that's classical in terms of our definitions of acids and bases for the Bronsted-Lowry definitions. Which one transferred my proton? Well, the water did. So if you compare that to the conjugate base, water, the conjugate base is hydroxide. Ammonia accepted that and it became the ammonium ion. But now if we take a look at my lone pairs, so if I redraw this, then I have my NH3 here, but that lone pair became the bond to my hydrogen. So what does this mean for us? What this means for us is that I formed this bond from the donation of this lone pair. So what we find then is that when we classify a base, this is not only a Lewis base, it's also a Bronsted-Lowry base, okay? So we have a consistency with our definitions. So what we find is Arrhenius is the most specific, then we have Bronsted-Lowry, and the most general would be Lewis acid-base definitions. But under the Lewis acid-base definitions, we will find our Bronsted-Lowry and our Arrhenius acid bases. So ammonia is my base and water is my acid. Okay, and in particular, it's one of the hydrogens of water that accepted the lone pair electrons to form that bond. Okay, now if you compare what happens here, in this case, ammonia donated its lone pair electrons to form a bond to the carbon. So that's this bond right here. Okay, so since my formaldehyde accepted the lone pair electrons, this is considered the Lewis acid. In particular, we're focusing on the carbon. And ammonia is my Lewis base because it donated the pair of electrons. So that's how we assess what's a Lewis acid and what's a Lewis base. When we see there's a difference in a bond in our product, and where did that bond come from? It came from this lone pair. Oh, wrong bond. If we look at this bond here, okay. So we're looking at this bond here. It came from this lone pair. And that's why we compare it so we can identify that ammonia is the base and the formaldehyde is the acid.